The question that I have is, could you describe the stress path followed by soil during triaxial and 1D compression loadings? I want to consider a few selected stress paths that could be simulated in a triaxial loading setup. We know the triaxial loading is a principal stress loading, right? It's not a general principal stress loading. It is a specialized principal stress loading where two of the three principal stresses are equal to each other. And therefore, for the purpose of analysis, this is basically a 2D loading. So we typically consider the sigma 1, sigma 3 space. So since there are only two stress components, sigma 1 and sigma 3, we could plot the stress path in the sigma 1, sigma 3 space. Some people do that, but it's more common to plot them in a different stress space, namely what we call a PQ space. Let's define P as the average of the three principal stresses. So that will be sigma 1 plus sigma 2 plus sigma 3 over 3, right? But because sigma 2 equals sigma 3, P then becomes equal to sigma 1 plus 2 times sigma 3 over 3. Let's define Q as the difference between the two principal stresses. And if you recall, this is what we called deviator stress or deviatoric stress, right? So here I would refer to this as deviatoric stress and P as the mean normal pressure. There are again two different definitions of these, but this is the definition that I would use in this course. This definition is sometimes called the Cambridge definition because when the researchers developed the Cam-Clay model back in the 60s, they used these definitions. Now back to the topic of interest here. So instead of plotting the stress path in the sigma 1, sigma 3 space, I'm going to be plotting the stress path in the PQ space. That is, we'll be plotting the stress path in this space right here. Now let's consider some specific loading that we could potentially do in a triaxial setup and see if we can plot the stress path during such loading. First, let's consider consolidation loading. Remember we said earlier a standard triaxial loading consists of two phases, consolidation phase and the shearing phase, right? So I'm talking about the consolidation phase here. So how do we do consolidation? Well, we increase the cell pressure, right? So if I want to consolidate the specimen under, let's say, 100 kilopascal, we would gradually increase the cell pressure from 0 to 100 kilopascal like I have shown in this picture right here. Cell pressure is an all-around pressure and therefore sigma 1 and sigma 3 will increase simultaneously and therefore during the loading sigma 1 equals sigma 3. Now I'm interested in plotting the stress path as we go from stress state 1 to stress state 2. And I want to plot the stress path in the PQ space. These stresses would allow me to locate point 1 in the PQ space. And similarly, these stresses would allow me to locate point 2. But the key to predict the loading path is this relationship right here. Now I utilize the definitions of P and Q in conjunction with this relationship in order to arrive at these equations. So P works out to be equal to sigma 1, Q works out to be equal to 0. The values of P and Q at point 1 are these, 0, 0. At 2, P is 100, Q is 0. And I got these from these equations right here, right? So point 1 plots here, point 2 plots here. And then during the path, Q has to remain 0, right? So Q is 0 always. And therefore, the only way to get to point 2 from point 1 is horizontally along this path right here. So this is the stress path that we've been trying to plot. Now let's consider the other part of the standard triaxial test, which is triaxial shearing. Say the specimen has been consolidated to a consolidation pressure of 100 kilopascal. The cell pressure at this stage is 100 kilopascal. Now we are increasing the deviatoric stress in order to shear the sample. If you increase delta sigma, we call this a compression test. Also in a standard test, we don't change this. So sigma 3 remains to be sigma z during shearing. Again, using the definitions of P and Q and the specific way in which we vary these stresses, I arrive at these equations for P and Q. At point 1, delta sigma is 0, so we get these expressions for P and Q. At 2, we just leave it as is. So what I have done here is that I have evaluated delta sigma from this equation and then put that in this equation in order to arrive at an equation that looks like an equation of a straight line, right? In other words, y equals mx plus c kind of equation, right? So in our case, our y is really q and x is p. So you can see it's an equation of a straight line. It has a slope of 3 vertical to 1 horizontal, which is this part right there. Point 1 plots here, point 2 plots there, and at point 2, our q is simply the deviatoric stress, and P changes from sigma c by delta sigma over 3. So if I were to use some numbers here are the calculations. So in this approach, I had to combine these two equations in order to figure out the equation of the stress path. It turned out to be a straight line. So now I know I can connect point 1 to point 2 by a straight line, right? And I could have done that in a slightly different way, which I call here as the alternate way. What you do is you consider the changes in stresses from state 1 to state 2. So you can see delta sigma 1 changes only by this much, delta sigma, all right? Delta sigma 3, which is the change in sigma 3, is 0. Sigma 3 does not change, right? And therefore that is 0. So now you put these two expressions in the definitions of P and Q. In order to get delta P and delta Q, we get these. All right, so from these, it's easy to see that the ratio between delta Q and delta P is 3, which is a constant, right? So we know the slope is constant, and therefore what kind of mathematical function has a constant slope? Straight line, right? So we figured out the slope simply by considering the changes as opposed to the total quantities over here. Now I'm going to consider another kind of loading that could be conducted in a triaxial setup called anisotropic consolidation. At state 1, the specimen is stress-free. Now we are going to increase sigma 1 by delta sigma 1 and sigma 3 by delta sigma 3 in such a way that the ratio between delta sigma 3 and delta sigma 1 remains a constant k. Can you guess what this value is for the consolidation that we do in a standard triaxial test? What do we do in a standard triaxial test? Well, we increase the cell pressure, right? So sigma 1 and sigma 3 increases by equal amount all the time. So something like that is what is called isotropic consolidation. So because both delta sigma 1 and delta sigma 3 are equal to each other, K is basically 1 for isotropic consolidation. K will be different from 1 for anisotropic consolidation. So here I'm going to take the second approach that I mentioned in the earlier slide in order to figure out the equation of the stress path, which is to consider the changes in the stresses. We know sigma 1 changes by delta sigma 1, sigma 3 changes by delta sigma 3, and then utilizing this equation and the definitions of P and Q, I arrive at these equations for delta P and delta Q. So I express these in terms of delta sigma 1, and when I take the ratio between delta Q and delta P, the delta sigma 1 terms cancel out, and I end up with this expression for delta Q over delta P. Since K is a constant, this ratio is also a constant. So let's call this as eta here. Now I evaluate the values of P and Q at point 1, which of course is 0 because the specimen is stress-free at point 1. And at 2, P will simply be equal to the change in P, right? Because it starts from 0 value for P. And similarly, Q will be equal to that. So if I give you a number for delta sigma 1, you can evaluate numbers for P and Q. So we have the initial point, the final point, and the path is a straight line because this ratio is a constant. So here is the stress path in the PQ space. It's a straight line starting from the origin. So this is state number 1, this is state number 2, and it goes along a straight line. And something like this is what is called a radial stress path in the PQ space. The straight line has a slope of eta. Eta can be calculated from the knowledge of little k. I calculated the values of eta for different values of k here, 3 values, and I plotted the stress paths during anisotropic consolidations with these k values. Of course, k is the stress ratio, right? Ratio between the horizontal and the vertical stress. You are probably wondering as to whether it is possible to do something like this in a triaxial cell, right? Well, you simply have to increase the cell pressure simultaneously as you increase the vertical stress. If you were to do this manually, it's not that easy. But most machines these days are computerized, so it's much easier than you think. Another question you're probably thinking of right now is, why do we do a crazy thing like this? Remember we said soil is a plastic material, right? Elastoplastic to be precise. So its behavior depends on the loading path, right? So it turns out the loading that takes place in the field is generally very complicated. When you apply a column load on a shallow footing, different points below the footing is undergoing all kinds of complicated loading. It is nowhere near the triaxial loading that we normally perform in the lab in order to evaluate the stress strain behavior of soils. So the loading that we apply to a laboratory sample doesn't seem to be close to what's going on in the field. So every now and then you wonder whether you are barking up the wrong tree. So this is where researchers like me come into the picture. We try to conduct experiments in the laboratory utilizing stress paths that are a little bit more realistic. We do this, number 1, to learn the basics, number 2, to incorporate the observations into a suitable mathematical model that could be later used in something like a finite element analysis. In the next slide, I'm going to show you the loading that takes place in one of the common things that happens in nature is anisotropic consolidation. One of the ways in which the horizontal soil deposits that we see today were formed long time ago was from soil suspensions. They consolidated under their own weight and leading to what we now call the normally consolidated soil deposits. The loading process is pretty similar to this. In other words, if I were to put a soil suspension in a cylinder, like a consolidation cylinder, right, and provide some drainage over here and here and consolidate this, right, eventually I'm going to get a normally consolidated specimen out of this, right? But it turns out during this process, during this consolidation process, the ratio between the horizontal and the vertical stress remains a constant. And this is what we call K naught. And sometimes something like this, the consolidation that we perform in a one-dimensional cylinder is called the K naught consolidation. Now let's go back to what we talked about in the earlier slide, stress paths, right? So what do we have here? We basically have anisotropic consolidation. So this is what happened in this soil deposit millions of years ago while it was being formed. Since we are at this, we might as well talk about what happens during unloading as well. So we are considering the stress paths during K naught loading, unloading. So what exactly are we doing? Well, we put some soil slurry into a cylinder, consolidate it by increasing the vertical stress, and then unload it back to 0. If you're wondering what's so special about this type of consolidation, what's the boundary condition? The horizontal strain during this consolidation is 0. And for this reason, and this is also called one-dimensional consolidation. So here is the experimentally established fact. This is the sigma 1 prime, sigma 3 prime space. Let me emphasize that these will have to be the effective stresses, not the total stresses. So anything that we're going to talk about here applies only when you plot the effective stresses. So 1 to 2 represents loading, and then 2 to 3 to 1 represents unloading. So what do we see here? Well, we have a straight line from 1 to 2. That means the ratio between sigma 3 prime and sigma 1 prime is a constant during loading, and therefore K node is a constant. So if I were to plot the variation of K node with sigma 1 prime during loading, I'm basically going to get a horizontal straight line. So it's a horizontal line from point 1 to point 2. 1 represents this, 2 represents this. The value of the K node during loading depends on the soil type. But if you're looking for a value, rough value that you can use, it's around 0.5. So coming back to this again, the unloading relationship is not a straight line. And therefore, the ratio between sigma 3 prime and sigma 1 prime keeps changing. That means K node is no longer a constant. What's the value of the K node at this point? Well, this line has a slope of 1 to 1, basically a 45-degree line, right? So at this point, sigma 3 prime equals sigma 1 prime, and therefore K node is 1 at that point. So you can see that K node has increased from something like 0.5 over here to already 1 at 0.3. We are not even done unloading completely. So at points below 0.3, K node is actually greater than 1. You might be wondering about the practical significance of this, right? Well, when we unload, what are we doing? We are over-consolidating the soil. And therefore, soil at these points are over-consolidated soil. So what we are seeing is, while K node is a constant for a normally consolidated soil, regardless of the existing stress, the value of the K node for an over-consolidated soil depends on the degree of over-consolidation ratio. At this point, over-consolidation ratio is 1, but then it just keeps increasing, right? And we know K node also keeps increasing. So it could be as high as 1 or even greater than 1. So how does the stress paths look like in the PQ space? So 1 to 2 is pretty straightforward. It's loading, K node is a constant, and we covered this in the earlier slide, right? So we get a stress path that look like this, a straight line from 1 to 2, a radial line in the PQ space, right? So I'm going to sketch the unloading path in a qualitative sense because obviously it is a curve and it's not that easy to quantitatively do it. We can do it if somebody gives me the experimental data, then we can pick points over here and calculate the P and Q at various points and plot it. But for now, let's discuss this in a qualitative sense. We know at point 3, sigma 1 prime and sigma 3 prime are equal to each other, and therefore by definition Q has to be equal to 0, right? And therefore 3 plots right here. And at points below point 3 all the way to point 1, sigma 1 prime is smaller than sigma 3 prime, and therefore by definition Q is negative. So the part of the curve from 3 to 1 falls in the negative direction, negative Q axis. So the overall loading and the unloading path during a one-dimensional consolidation look like this in the PQ space.